Hi, everyone, and welcome to today's Plant Services webinar on motors and drives, sponsored by Timken Power Systems. I'm Tom Welk, the Editor-in-Chief of Plant Services, and I thank you for joining us today. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please put your question in the questions window, and our technical experts will assist you directly. We also recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. Simply type your questions for the speaker into the questions window on the side of your screen and hit the submit button. Today's speaker will respond to those questions in the time we have remaining after the main presentation, and any questions that we don't get to in today's presentation will be taken up one-on-one via email. If you'd like a copy of the presentation today in the form of a PDF slide deck, please click on the Event Resources tab on the side of your screen to download the presentation. Also available in this section are a brochure on supplying and servicing the drivetrain and a link to several videos from Timken Power Systems, including one on industrial drivetrain repair services. Please be aware that today's session is being recorded and will be available on the Plant Services website within the next 24 hours. You'll be notified by email when the archive is available to either rewatch or share with your colleagues. And now let's meet today's speaker. I'd like to welcome Henk de Swart, who will speak on the topic of how to use testing to ensure the reliability of aged synchronous motors and generators of 4,000 to 35,000 horsepower. Henk has served as the Chief Electrical Engineer at Timken Power Systems since 2019 and is responsible for technical support to Timken's 3 electric motor repair workshops, where he conducts failure investigations and root cause analysis on high-profile cases. His extensive practical experience has allowed him to author 8 published IEEE papers, invent 9 registered U.S. patents, design many unique motors, and complete technical audits on more than 30 of the major service shops in the U.S. Henk, welcome. It's good to see you. Thanks for being here today.
Good afternoon. Thank you very much for the opportunity. It's great to be back. And this time we're talking about larger machines. So stepping right into it, if we talk about these large machines, when considering electric power generation, one often thinks of 100 megawatt or greater generators. While those power ratings are commonly used in large commercial gas, coal, nuclear power plants, there is also a significant installed base of power generation and conversion synchronous motors and generators in the range 4,000 to 35,000 horsepower. These machines are too small to fall in the traditional power station class, yet they are critical for power generation and conversion in paper and pulp, petrochemical, metal, steel, and many other industries. This class of motor and generator generally can run for many years after they've been installed with very little maintenance. But years after the original installation, possibly after an unplanned trip, the maintenance staff may realize these machines do need maintenance to ensure long-term reliability. Frequently, large capital projects are specified and installed by project teams who, after completion of the project, move on to the next big project, leaving the production staff with a new baby in hand. The production staff typically are under pressure to ensure that the shiny new plant runs smoothly and produces maximum output for the first X number of years until the first major planned outage. The initial running period typically ranges between 4 and 8 years. By that time, everything that should have been done annually for maintenance, according to manual, may not have been done. This is if anybody can still find the manual. The plant staff then turn to their trusted electric motor service workshop personnel who, for instance, may also find that this is the first time they see this dark machine that's been hiding somewhere in a dark room for several years. In instances like these, the production staff typically cannot rely on the original plant project team or equipment OEM to assist with the testing and maintenance of this huge machine. To fill this gap, this presentation provides the end user and plant owner with specific information regarding an important part of the maintenance cycle, how to use testing to ensure long-term reliability of synchronous motors and generators. We will, however, use the term motor and generator interchangeably. This presentation doesn't intend to be an exhaustive study on the testing of large generators, since that would require a significant volume to study. However, we will provide the user with some insight into key tests to be performed as part of the maintenance cycle and how they actually work. Investigating the cost of planned maintenance versus unplanned costly downtime, the plant will probably come to the same conclusion as many publications, that unplanned downtime costs far exceed planned maintenance costs. However, poorly structured maintenance can waste costly additional time and unnecessary maintenance. There are many different generator construction methods. This presentation shows some of the common designs and the recommended testing to be performed for large synchronous motors and generators, typically in the range 4,000 to 35,000 horsepower, although these can be extended to smaller and larger machines. Each individual machine's scope of work should be customized for the specific machine design. Now, if we look first at the construction of the generator, I want to show you a couple of the inside, guts of the generator that will hopefully help you to understand what I test and how I test. So the intention is not to teach you how to perform the test, but when your service workshop do the testing, that you can make sure that they perform the test in the correct manner, looking at the correct information and using the correct test equipment. So shown on the screen, on the right-hand side, you will see the stator winding on the inside of the machine. Right on the inside, you will see there's the stator core. And we will go through each of these different components. The core is the magnetic circuit where the flux flows through. Then you'll see the winding that sits inside the core. And of course, on the outside, there is the frame that houses and put everything together. Now, this is a beautiful 32 megawatt generator that we rewound a couple of years ago. Now, you will see on the winding, there's a portion of the winding that's outside of the core that's easy accessible. And then you'll see there's a portion of the winding that's inside the core, which you can't get to. You can't even see it. There's a wedge that protects it, but it's still there. It's a very important part of the winding. On the left-hand side, you will see a bare core. In other words, when the stator winding is being removed or it's a new core, this is how the core will look. It's not solid steel. It's, in fact, thin lamination plates that are stacked together, but they are also insulated from each other. If this insulation breaks down due to a failure, heat, damage, rust, physical damage, if there was a core up, then the losses in the core will increase and the core temperature will increase. Moving on to the stator winding. Now, on the left-hand side, I show a typical construction as the coil exits the core. On the right-hand side, I've got a cross-sectional area to explain the different components that you can then also match the picture on the left. So first on the inside is the conductor, which is typically copper, which conduct the electricity. Very important because without that, obviously, there is no power. Around that is a conductor covering. This could be an enamel. It could be some sort of epoxy resin around glass, or it can be a tape. Then around the conductors that forms a turn, there's a turn insulation. This is not always the case. So some OEMs do not use turn insulation because they make the conductor insulation thick enough to compensate for the voltage. Around that is the main wall insulation. That's almost the most important part of the insulation that insulates the copper or the conductor from the core. If that insulation breaks down, you will have a short circuit between the core and the conductor, and you will have a big bang because all the energy will then create a ground fault, which could most certainly damage the stator winding, but could cause significant damage to the core, which can be costly and take a long time to repair. So the main wall insulation is made up of typically mica-based insulation that's taped around the coil in multiple layers, typically about 1/2 lap layer per kV of voltage. Around that, you will see the black tape, and literally it is black, and many people call it black tape, which is called a corona shield. On the left-hand side, you will see that it's shown in purple for some strange reason, and it is just inside the core and just exit the core slightly. Now, the purpose of this is quite strange. It is not insulation. It is, in fact, conductive tape. So it's a glass tape with some carbon in it, and it forms a conductive surface between the coil and the core. Because what we found is if there's air between the coil and the core, you get partial discharge, which is high-frequency discharge that will damage the insulation significantly and lead to a failure. Normally, partial discharge failures are long-term failures. You're looking 8, 10, 12, 15 years, but still, it can lead to a failure. The next thing you get is the gray tape, which is also gray. Number 6, the stress grading tape. And on the left-hand side, you will see that it's actually outside of the core. Now, what happens is the reason for this is at the end of the corona shield, which is conductive, which effectively extend the ground plane from the core, you need to then grade the voltage, because in the coil, you have the full voltage, and at the core, you have ground. So you have if you think of how lightning works, you have a point where the lightning strikes. And that's exactly what you try and prevent, that you have a point where there's the steep gradient between the ground voltage and the full voltage. So this gradient tape actually grades the voltage gradually over the overhang. So it's very, very important from the long-term health of the insulation. Like I said, the idea is that I explain to you what these things are, and then when we look at the test, we can identify, but why am I performing this test? And then you will understand better how to interpret the results. Now, if we look at the rotor construction, we'll see there are two distinctly different rotor types. On the left-hand side is what's called a cylindrical rotor or turbo rotor. Now, those are typically used in 3,000 RPM or higher speed machines. I have seen them occasionally in 1,800 RPM, but those are extremely expensive machines. They are extremely robust. They last for decades and decades. Very, very good machines, but crazy expensive. Now, the reason why you would use them, even though they are an order of magnitude more expensive than the other rotors, is because of the centrifugal force. When you rotate that large rotor at such high speed, the windings wants to come out of the slot. And I'll show you what is the specific constructions that will help to keep the winding in the cylindrical rotor. You can, in fact, you can't even see the winding. It's inside the core. There's this weird thing on the end that's where the overhang of the winding is supposed to be. You can't see the winding. And that's important because when you try and clean this machine, you basically can't. Even if the rotor is outside of the stator, it's very difficult to clean this rotor. Because often when you try and use air or dry ice, you may actually just blow contamination into the winding. So if you need to clean this winding, it is a very big deal. We always recommend that the rotor should be taken to a workshop to be cleaned there. Because if you take off the rings on the ends, the winding relaxes and you won't get it back in. In any case, more of that later. On the right-hand side, you will see a salient pole rotor. Those are typically 4-pole and slower speed, in other words, 1,800 or less RPM machines. You can see that the winding is easy accessible. You can see the poles, which the conductors are wound around. These conductors could be round, they could be square, they could be flat pieces of copper, but they're easy accessible. You can see them. It's easy to see what's going on. Let's move on to the next slide. So on the left-hand side is another salient pole rotor core, but here you can see it, the construction is quite different. There's more poles. You, in fact, can count the number of poles. you can look and count each of them and see that this is what, 16 or 10 pole. And you can see again, the rotor winding is exposed, it's easy to see. These pole pieces are also removable. Sometimes they are bolted together, sometimes they have dovetail wedges. So this type of rotor is much more easy to perform maintenance, but also much easier to test because you can get to everything. On the right-hand side, you will see how the cylindrical rotor body looks. It's milled from solid steel. So that's one part of the expensive cost of it. And there's very little testing you can do on it. You can do non-destructive testing, but you can't perform core testing or anything like that. Now, if we look further into the cylindrical rotor, we see there is the core on the right-hand side. And then to maintain the winding inside the slot, there are wedges. Now, these rotor wedges are different from stator wedges. Stator wedges are normally from a type of epoxy wedge because they don't need to retain the rotor that has to counteract the centrifugal forces. Now, remember, these rotors are normally 3,000 RPM and higher speeds. So the centrifugal force on the winding that wants to get out of slot is extremely high. So these wedges are typically from a high-strength alloy. They're non-magnetic. It's typically like a beryllium alloy. Often they would have ventilation ducts in them, and if these ducts are blocked, then you could have problems with ventilation and cooling of the machine. On the right-hand side, you will see the end rings. Those are the rings that sits over the winding that keeps the winding together and inside. Again, these are from ultra-high strength non-magnetic stainless steel, and they need to counteract the centrifugal force. Now, going into what kind of things we are looking at. Firstly, absolute most important of all the tests is visual inspection. People don't think it, but it's actually been found in many studies, and I've personally experienced on site looking at many, many different machines, a visual inspection. Look for contamination, look for oil, look for dust, look for things that discolored. If I look at a stator core and there's an area that's been discolored, that means there's a problem there. So visual inspection is absolutely key with all the testing that you do. So both on the rotor and of the stator, visual inspection is key. Now, sometimes you might decide not to remove the rotor from the stator. Then you can see very little. On the cylindrical rotor, you can see almost nothing. You can only see the end bells, where on the salient pole rotors, as you can see on the right-hand side, you'll be able to see the pole caps, you can see the winding, you can see the insulation, and all of this you can do a detailed visual inspection. In the middle, I say cleaning. Often we try and perform testing on the machines, but then the winding is dirty. And all that you will get is a result that says the winding is dirty. So as part of the assessment process that I will discuss right at the end, we highly recommend that you clean the winding to make sure that the test results that you get actually makes sense. And cleaning of the winding is absolutely critical because part of the machine failure rates is related to team stresses, which I will discuss later, and part of that is temperature. If the winding is contaminated, it's insulated thermally, so it prevents the transfer, but it also reduces the airflow. Now, if we look at the test methods that we're going to be discussing, first we'll look at some traditional test methods. Hopefully you've at least heard of these test methods, most of them, and then we'll go into some more advanced. Now, so for each of these, I will go through the test, explain basically how the test is done. Like I said, the intention is not to train you how to do the test, but more to what to look for. The resistance test applies to the stator and the rotor winding. Now, typically what you do is you would apply a voltage to generate a current, a DC current through the winding, and you will measure the voltage and calculate the resistance. So the resistance is of the winding. It's not of the insulation. It has nothing to do with the insulation. It is only in the winding. Now, on the right-hand side, you will see at the bottom where I show the circuit diagram, you can measure different types of resistances. You can measure the line-to-line resistance, RL, I show it, where it's basically you get the resistance of two of the phases. Or on the left-hand side, you can measure the phase resistance, which is of only one phase. Now, this is an important test. It's very important that it's done correctly. Typical instruments that you can use, and these are just examples of Fluke, Tinsley, or Ductor. They make resistance meters. Surge tester, for instance, a Baker, where they've gone through multiple iterations. Electron, P&J, and TIG, or a combination tester, for instance, a PDMA. Things you should not use to test the resistance is a normal multimeter. If you look at what I said, what is the requirements for the test? You need to supply at least 1 ampere. Because these are very large machines, the resistance value would be very, very low. And if you try and just use a normal multimeter, it only supplies a very small current, so the voltage that it measures is very, very small, and it can't do accurate measurement. So you want something that generates at least 1 amp into the winding and have at least 3 significant digits of reading. And I'll show that to you later why that is. Now, typically installation or resistance test, the acceptance criteria is between 3 and 5%. It's almost impossible to use this test to try and find a winding short. People think that is what it's for. It's not. It's actually basically testing continuity of the winding. So if you think of a stator winding with, say, 72 slots, 72 coils with 10 turns per coil, that gives you 720 turns, and you have 3 phases, so that's what, 280 turns per phase, and you measure the phase resistance, you get a value. Now, if each winding is 280 turns, the resistance should be equal. Now, if you have a turn-to-turn short, and one winding has got 279 turns, you can see that the difference is less than 0.5% in the resistance. That's why the resistance test is not primarily intended to look for an inter-turn short. Now, let's look at another one that you will probably know. The insulation resistance test is very well misunderstood. Lots of people think that the insulation resistance test and polarization index test, which is next, is used to quantify the condition of the winding. This is the best. No, it's not. You would use it before you want to start the machine. It is a fair indication of what the contamination of the machine is, primarily with respect to moisture. Now, if you look at the diagram on the right, you can do 2 types of tests. You can do the winding to ground, which could be a phase if there's 6 leads out of the winding and you can split the winding, or you can test between the phases. Now, if you think back of your stator, if you do a winding to ground test, in reality, where you are testing is between the core and the winding in the slot. It has very little to do with the overhang of the winding. And where is the contamination on the winding? Primarily on the overhang, because that's where the dust can settle. In the slot, in the core, it can't get there, so it can't settle there. So your insulation resistance is looking at the resistance between the conductor and the core, but very little on the overhang. Now, what do you need for this instrument? You need to make sure that it shows the actual test voltage. This is to ensure, especially on large machines, if the capacity of your test instrument is too low, it might tell you it's testing, you set the setting to 5,000 volt, but it might not be testing at 5,000 volt because it doesn't have enough capacity. Now, tests that you can typically use is, for instance, a Megger. That's why lots of people know this test as the Megger test, is because Megger was the first commercial instrument that was actually used for this test. So lots of people would say, I'm going to Megger the motor, which they're actually referring to is the insulation resistance test. Fluke also makes a nice tester. You can use your surge tester, for instance, the Baker, Electron, P&J, or TIG, or a combination tester, for instance, PDMA. Instruments that you should not use. Again, the multimeter. The multimeter is great but it doesn't have enough capacity to measure the insulation resistance and the hand-wound insulation resistors. If you remember back to when you were in college, probably you took the hand-wound insulation resistance meter, wound it up on a capacitor until it blew up. That was fun and games. But the capacity is way, way, way too small to be able to effectively test such large generators. Now, the polarization index test is related to the insulation resistance test, where you will have a 10-minute value, and the insulation resistance is a 1-minute value. You divide the two by each other, and then you will know what is the polarization index value. It doesn't have a unit of measure, it just has a value. Typically, you want to be above 2, and it gives you an indication, basically, if there's a lot of moisture contamination in the winding. If there's lots of moisture, the polarization index might be below 2. Insulation resistance would probably also be low. The risk is that if you don't have moisture, the winding can still be severely contaminated on the overhang, because remember, your insulation resistance is measuring between the core and the winding in the core. So I've seen machines that are outside, the overhang is almost completely blocked with contamination, and the insulation resistance is fantastic because there's no moisture. This could be a big problem in plants like cement plants, where the cement is dry, so it has very little influence on the insulation resistance, but again, it prevents the machine to run cool. It reduces the cooling efficiency of the machine. Moving on to a surge test, a little bit more complicated test. It's applicable to the stator winding only. What it is, you apply a high-frequency impulse is applied between the winding and earth. The impulse response is plotted in a graph, and the curves are compared between the different phases. So this is typically also called a surge comparison test. The test specifically tests the interturn insulation. In other words, that insulation around the conductor. It does not test the main wall insulation. Now, what do you need to look for an instrument? The instrument must show the actual test graph and the test voltage. Now, you will see on the right bottom that you can test between different phases. And I'll show you some of the test results a little bit later and how that you can see there is a problem. This test is absolutely critical to test. It tests at an elevated voltage. In other words, it's not at the low voltage like the resistance. You can test at the machine design voltage, and you can even exceed the voltage, and it specifically looks for that interturn short or weakness as well, which your insulation resistor cannot check at all. Remember, the insulation resistance meter will measure between the conductor and the core, and the surge test measure between the turns in the conductor. Now, the instruments that can be used is the surge tester from Baker, Electron, P&J, and T. Combination testers should not be used. They are not suitable for this. Now, looking at some of the test instruments, the first is a resistance meter. Remember, I said you need significant instruments. I pulled this drawing from a photograph I took at the Isovolta, which is one of the leading manufacturers of insulation in the world, when I was at the plant in Austria doing research on our new insulation system. And their resistance meter measures to 4 significant digits after the decimal point. So it's 7 decimal significant that it can measure, which is absolutely incredible. But obviously, that's a laboratory. On the right-hand side, you can see an insulation resistance meter, a typical one, like I said, a Mega or Fluke, something like that. Now, if we look at the surge tester, those are typical examples. The Baker is one of the big boys, the old guys in the industry. On the left-hand side image, you'll see it's got the power pack, and a power pack actually increases the output voltage from the typical unit, which is 12 kV to 40 kV, to be able to test larger machines. In the middle is a different one that's called the AWA, which is also from Baker. It's used to do winding analysis. And on the right side is one of the old original TIG winding testers. A Surge tester, incredible machine. I tested with them as a young engineer. They do the exact same thing. You just can't do a digital recording of the values. Now, looking again at the insulation resistance tester, the images there is shown of a test screen. And what you want to look at, as I've highlighted in that box, is that I can see the actual test voltage. And like I said, this is one of the key points when you look at the insulation resistance testing, is that the test instrument has to be able to measure the test voltage. It's not just a setting that you turn to 5,000 volt and then hope that it does test correctly. You need to be sure it tests the correct voltage, especially on large machines where you require significant capacity to test. Now, looking at the surge test, I've got two graphs. On the left-hand side, you will see the graph of a machine that's in good condition. You can see there is the graph. You can actually just see one graph because on the top right, you will see 1 to 2, 2 to 3, and 3 to 1 has got very low percentage deviation. Now, that's a correlation calculation that if you have one of the newer surge testers, that it calculates those values, and it will show you if it looks good. All of the graphs are on top of each other, so it's good. If you look at the right-hand side, that's a failed surge test. And if you look clearly, you will see that one of the graphs is offset from the other two. And that is an indication of a problem in the surge test. In other words, an interturn fault. Okay, so let's move on to a little bit more advanced testing, but still a traditional test method is the RSG, or repetitive surge generator, or recurrent surge oscillator, many different names. It only applies to the rotor. It's sort of similar to the surge test on a stator. However, this is a low voltage test that you apply. Now, remember, on a synchronous rotor, you basically have one winding. There's no three phases. It's a DC winding. So it's very difficult to test and compare. But what the RSG test does, it tests the winding from the one direction and then from the opposite direction. And the idea is that the impedance from both directions should be the same. As you can see on the screen, there was a problem with this job because there is a deviation in the graph, similar to what we saw at the stator. One very, very interesting thing about this test, it is extremely sensitive. I've done multiple tests where I take a winding that might have 400 turns in it or 800 turns, and I short out only 2 turns, and you would actually see it on the graph. Immediately it shows up. So a very sensitive test. A big advantage of it is that it can be done with a rotor installed, with a rotor outside. You can't do it while the machine is running, though. But one interesting thing that you can do to it is when the rotor is in a balancing bay and it rotates, if you use brushes that you supply onto the slip rings, you can actually perform this test while the rotor is rotating. Very, very important, especially after a rewind. So you want to make sure there's no interturn shorts that's in the winding that occurs only when the winding moves. Remember, the centrifugal forces will push the winding and it will move during rotation. On 3,000, 3,600 RPM, that is even more important because the centrifugal forces is so massive, the winding moves a lot. So this test you can, and I've done this on a 36 megawatt, 3,000 RPM rotor that I tested. Pretty scary to do it the first time, but it was great to be able to make sure that there is not an interturn short on the rotor. Now, another traditional test, this is the one you probably use to, is the volt drop test. Basically, you supply on the winding on the 2 incoming leads, and then you will measure the voltage drop over each pole, and you compare them. Now, it attempts to do to check for interturn short. Now, you can see on the cylindrical rotor, you can't do this. It's not possible because you can't get to the individual poles. On a cellular pole rotor, you will test them each pole individually, measure the voltage, and then compare them to each other. It could create a false sense of security, because if you think again of the case where there's so many turns, if there's only one turn different, then the voltage difference won't be that much. But still a very useful test to do, quite easy to be done. The rotor needs to be outside of the stator, but very easy. You can literally run the test from a wall plug. That's how easy you can do it. Okay, another important test, which on large machines, and that's why I bring it up. Normally on site, you will not perform this test, the core test, but on very large motors and generators, when you remove the rotor, you might want to do a core test. Typically, this can be done with either applying full flux, which is really difficult on site, or LSID tester, which is a very sensitive Hall effect sensor that measures the losses in the core and specific point. Fantastic test to be done on the stator. Normally, you would only do that if you see a problem. Like if you look at the machine, the stator winding has not failed, I've cleaned it, but there is signs of temperature damage. There's discoloration of the laminations, or I had a core rub. Then you want to do this test to make sure that there's not there's not shorts between the laminations that will cause heating problems in the core. Now, if we look at a little bit more on the rotor side, non-destructive testing, it's called, not implying that the other tests are destructive, but these normally are called this because they are more of a mechanical test. Now, if we look at the cylindrical rotor, we will do on a coil retaining ring a dye penetrant test. This is very important to perform during a normal maintenance cycle, typically an 8-year maintenance cycle. It's quite easy to perform on site. However, you need to remove the rotor. Because what happens, because of high centrifugal forces, they might start to develop microfractures in the coil retaining rings. Now, these develop over many, many years, but they can result in that coil retaining ring failing that will destroy the entire machine. It will rip the machine apart. So definitely something you want to make sure that your maintenance company, they do that at least every 8 years. Another test that you do, a shaft and fan dye penetrant testing. That is to check that there's no cracks in the fans and the shafts. This can be done to any accessible part of the rotor, even if the rotor is inside of the core. Now for the interesting stuff. These advanced methods I wanted to present to you today to show you what can and what should be done on these large machines. These machines cost hundreds of thousands or millions of dollars and produce 10 times that amount of profit for the company. So it's critical to know what are their conditions. So I want to present you 2 different tests. But before I go there, I want to talk about the insulation. On the insulation, it's subjected to what's called team stresses, which is thermal stresses, thermal aging, thermal cycling, electrical stresses because of the voltage, ambient stresses, which is moisture, chemical, and mechanical, which is vibration, torque, and movement. Now, these kind of stresses are there always, but I might be able to do things to limit them. Now, if we look at the graph on the left, what it depicts is at the top, the blue curve is the strength curve. This is the strength of the insulation over its life, over a time period. And at the bottom, you'll see the purple curve is the stress that this insulation is subjected to. Now, if the stress is a relatively constant, or the curve is curving up slightly, the strength will just go in a similar manner, decrease the strength. However, you have transient events. Transient events might be there's circuit breakers on the line that cause high voltage spike on the line. You might not even know that it's there, but it does electrical stress damage to the insulation. And therefore, the strength curve decreases in a step manner. Now, you can see if there are no transients or stress events, then the insulation would last much longer. But often, we can't really do much about these events. If the stress curve and the strength curve cross, at that point, failure becomes imminent. Before that time, however, there could be a premature failure. If the insulation is degraded sufficiently and a transient event occurs, it can result in the failure. So what we want to do is, when we want to ascertain the condition of the insulation, we want to try and identify these curves, both of them. And if we do that, hopefully we can try and predict the remaining life. Now, that is what the life expectancy analysis program does. It's a series of tests. It's very sophisticated. It requires advanced testing equipment of like 2 boxes of 500 pounds each. The testing takes about 10 hours to complete, and then the analysis takes weeks to complete. And what happens is there's a suite of about 4 tests that includes the tan delta test, offline partial discharge test, polarization and depolarization, current analysis, and non-linear insulation analysis. So all of these tests have been combined into a statistical model that then is compared to more than 25,000 of historical results of machines of any type you can think of and any size. The largest machine, to my knowledge, that's been tested is 1,000 megawatt or a gigawatt generator. Look, what happens here? The idea with the test is, if I can, at a point, as shown in that graph of the maintenance intervention, if I can identify what these stress factors are and then do targeted maintenance to eliminate them or to reduce the stress and increase the strength of the material, if you look at the dotted graph, effectively, I could increase the life of the machine because the strength curve will be higher and the stress curve will be lower, possibly avoiding the unplanned failures and also increasing the end of life. Now, to show you how this, some of the test equipment on the left-hand side, you will see there's a partial discharge. Lots of people know partial discharge instruments. And most of them would say, well, you need to track the results over years and then see what, and all of that is true. However, the LEAP test has taken all the data together with the offline partial discharge test that it will then give you a bunch of information. On the right-hand side, you will see the life expectancy curve where it shows, where the current with the degrading of insulation, what the life would be. And then if you do the targeted maintenance, you can extend the life by X amount of time. And in the graph in the middle, it will show you the condition assessment. So it's not just life prediction, but it's also condition assessment that can help you to target the maintenance, as in specifically what needs to be done. For instance, if the stress grading is degraded, you can go in, if you can get to the degraded stress grading, which is often the case, you can paint on new stress grading tape and you can reduce the stress on the insulation, thereby increasing the life of the machine. Incredible test. It can be done with the machine assembled and with the rotor inside. Now, another advanced test I want to show you is the rotor air gap inspector. Now, what it does is, the idea is on a large machine to look at the rotor sufficiently to do the visual inspection and the stator. I can't get to it, so I need to remove the rotor. This is costly, it's time-consuming, and expensive. Typically on a plant, this can take 5, 8, 10 days to take the rotor out and to put it back in. Now, the company has developed this air gap inspector, which is a robotic crawler that's mounted with rare earth magnets to the stator coil and controlled by an engineer, and have 5 high-definition cameras, and it basically runs in the air gap between the stator and rotor with the rotor installed. And then you can do a tremendous amount of visual inspection with videos, take photographs as well of the condition of the stator coil and the rotor winding, everything that you can get to that you can see. So it can have a significant advantage in cost reduction and time reduction of a maintenance intervention, and can help the plant to decide, do I need to pull the rotor? If I do an air gap inspection and I see, oh, there's a rotor wedge missing or a stator wedge missing, then I can do intervention that's targeted and not waste money. As I said and promised at the end, I'll give you an idea of the sequence of the tests that we recommend. First, you want to do insulation resistance and polarization index testing on a rotor and stator to get a baseline measurement. Then you want to, record the alignment of the machine, the air gap measurements. Then you want to do a dry ice cleaning of stator and rotor. Again, remember, I want to clean so that I can quantify the results that I can get. Again, I can only clean where I can get to, but I want to try and clean it as best possible. Then I want to do the insulation resistance and polarization index test again, so that I can compare the before and after. Then I'll do the resistance test on the stating, the surge test, and then I can do a leap test. Then if the rotor is removed, I can do a core test if I find somewhere there's a point of concern. On the rotor, I'll do the resistance test and the RSO test. Now, in conclusion, how do you use testing and to ensure the reliability of synchronous motors and generators 4,000 to 35,000 horsepower? I've shown you some common machine designs to help you understand what are the important parts of the machine that I want to test. I showed you the common tests to hopefully help you understand how these tests work, what type of equipment is required, and how to interpret the results. Then I've showed you some really fantastic advanced testing methods that can help you to determine insulation life of the stator, main wall insulation, and then a rotor gap, air gap inspection. So hopefully this, together with a customized scope of work, will enable you to effectively determine what kind of insulation testing you would like to do. And there's some references of the acknowledgement of the different suppliers, the testing suppliers, and there's papers based on a presentation a paper I wrote for the IEEE. Thank you very much. Now the floor is open for questions.
All right. Thank you, Hank, for that presentation. And we have 4 questions, Hank, so far that have come in. So I'll take this moment before we start the Q&A to invite our attendees. If you have questions for Hank on what you heard, whether it's about the advanced testing methods that he introduced to you today, or whether it's about other slides that he covered, go ahead and put your questions in the question box on the side of your window, and we'll get to as many questions as we can. So, Hank, I'll go ahead and advance the slide to questions and start with the very first one, which is, this one says, Hank, you mentioned surge testing, but can I not use an impedance tester instead of a surge tester?
Oh, no. Yeah, we get that question frequently. Impedance testing attempts to do what the surge tester does, but it tests at like 5 volt. Now, if you've got a 13,800 volt stator winding, testing at such a low voltage, unless there is a dead short somewhere in the winding, you will not see anything. These are large machines. You need to test them at an elevated voltage, even exceeding the supply voltage, so that you can find even weaknesses in the insulation before it has failed. So definitely not. Impedance tester, big no-no. Surge tester, yes. Thank you for that question.
Okay. We have another question. This one's about one of the more advanced test methods you covered toward the end of the presentation. This one's on the leap test, and it's the leap test that predicts the remaining life of the stator insulation. Sounds amazing. Can this test also be used on the rotor insulation?
Unfortunately, it cannot. The test is designed specifically for 4,000 volt and larger machines. And obviously on a stator, you won't have 4,000 volts. So unfortunately, it was developed specifically because it uses partial discharge measurements as part of the assessment condition. And on low voltage that's on the rotor, there is no partial discharge, so the test would be completely ineffective. Sorry, can't help you there. Great question, though.
No, that's quite all right. I like this third question a lot. It's about wind power generators, there's been a lot of attention on that lately. I've seen in the press. The question is, the newest wind generators that are installed tend to fall into the lower range of your presentation. They're 4 megawatts and larger. Do your tests also apply to these generator motors?
That's a great question. Yes, the tests do apply. Like I said, the leap test, you need to be 4 kV winding. The old style generators did not go to that high voltage, but these days we've seen 3 megawatt machines, 10 kV, 3.5 megawatt, 6.5 megawatt. That is 10,000 volt, 11,000. So yes, the leap test would apply. You will not practically be able to test the machine while it's in the nacelle. Definitely not. But the other tests, certainly all of the other test instruments is portable. So you can take a surge tester these days. Electron, the latest generation of surge tester is, the size of a small briefcase. And you can absolutely take it up in the tower. You can do a surge test, installation resistance test, polarization index, and resistance test all with one instrument. Absolutely, definitely you can do that. Great question. Thank you. Had me thinking there for a while.
Well, and this may be the last one of the day. I'm not sure unless someone sneaks a question under the limit. This is question number 4, and it's about insulation resistance test. What should be the acceptance limit of IR tests according to different voltages?
Oh, that's a great question. Thank you. Thank you for asking. The insulation resistance testing, all of these tests are governed by IEEE standards, apart from the lead test, which is a proprietary test. But the insulation resistance test is governed by IEEE standard 43. If you read the standards, it shows very much how it works and everything. They used to have acceptance criteria that was based on voltage. It was bad. It was, the voltage divided by 1,000 plus 1 mega. So for an 11 kV machine, it would be 12 mega. And the whole repair industry said, no, you are crazy. So after many years of us complaining, they changed the standard that the minimum acceptance insulation resistance is 100 mega. And definitely, before you start a machine, you need at least 100 mega. Although on a large generator, 100 megohm it's not great. I mean, it doesn't show that the machine is bad, but it could indicate that there is some contamination on the winding. You would typically see 3, 4, 500, even a gigaohm, but certainly at least the standard also says you need to have at least 100 megohm. But that's a great question. Thank you very much.
All right. And I've double-checked Hank and refreshed the question list, and I think that's it for today. So with your permission, I'll go ahead and move to close out for the webinar today. Hank, we'll start with you. Thank you so much for presenting today. I always enjoy working together with you, and it was great to see you at ESA. Thank you for being here.
Yeah, I enjoyed it. Thank you very much.
Let me also thank Timken Power Systems for sponsoring today's webinar and making it possible. One last reminder, you've got about 90 seconds. If you'd like a copy of the presentation, please click on the Event Resources tab on the side of your screen, and you'll find a PDF download of Hank's presentation today. Lots of great information there. Also available in the Event Resources tab are a brochure on supplying and servicing the drivetrain, and a link to plenty of videos by Timken Power Systems, including one on industrial drivetrain repair services. Last note, we encourage you to take a brief survey that will appear on your screen once we close out to provide some feedback that we can use to improve future events. So once again, thanks to Hank, thanks to Timken Power Systems, and thanks to everybody for being on today. Have a great rest of the day, everybody.
Thank you. Goodbye.